Hello, you welcome back. All right, so we are going to start with the of introduction to fluid mechanics. Okay, all right, and from what you see in this diagram, okay, fluid mechanics is actually divided into two parts. Okay, two categories. All right, we have the fluid statics and fluid dynamics. So now, question is, what is fluid mechanics? Now, as you can see here, this is a combination of two words, fluid and mechanics. Okay. Now, I believe you know exactly what mechanics. Okay. What mechanics is. Now, mechanics is actually the is defined as the application of laws of force and motion. Okay. So it's the branch of sciences or the branch of physics that studies the application of laws of force and motion. Okay, so which simply means that if we are having fluid mechanics, okay, so it's simply for us to join the two words together in this definition. All right, so it's simply this fluid mechanics simply um, can be defined as the application of laws of motion, right? Laws of motion and force on a fluid. Okay, so you can put it this way: the branch of sciences that studies the application of laws of motion and force on a fluid. So invariably now, the same way we have statics and dynamics and in engineering mechanics, we will also have fluid statics and fluid dynamics. Okay, so fluid statics, okay, fluid statics, as the name actually implies, okay, uh, is talking about fluid at rest. Okay, the study of fluid at rest. Why fluid dynamics, okay, is the study of fluid in motion. Now the question is, what is a fluid? How do we define fluid? Okay, now fluid. Now generally, fluid is of two kind, right? Anytime you hear of fluid, what should come into your mind is simply gas and liquid. Okay, so these are the two class of matter that actually falls under fluid, gas and liquid. So why do we classify gas and liquid as fluid? Okay, so that will now bring us to the definition of fluid, right? So fluid, all right, is defined as a substance, that deforms continuously. It deforms continuously on the application, okay, on the application of shear stress. So it simply means that if you actually apply shear stress on a fluid, okay, what actually makes it fluid is the fact that it will actually deform continuously when shear stress is actually being applied or exerted on it. Okay, so now please take note of that. So that is why we actually we categorize gas and the liquid as fluid. Okay, now the question is, what is a shear stress? Now I have to illustrate this, okay, this definition. Now before we actually talk about shear stress, okay, you should know there are two types of stress. We have the shear stress and the normal stress. Okay. Now, a shear stress is a stress that is acting normal to the surface of that particular object. Okay, so now let me actually illustrate this. Okay, now for me to illustrate what the definition, I'm going to compare um, the response of solid, liquid, and gas on the application of stress. Okay, so let's say we have a solid object. Okay, now there are type of stress you can actually apply on this solid object. All right, this is solid. It's either you apply a stress known as a type of stress known as normal stress. Now, now the stress, of course, a stress is actually a force or a load that is actually exerted on an object. Okay, so if you apply a stress on object, depending on the amount of stress and depending on the resistance of this object, what happens? It will deform. Okay, if the stress is normal, so this simply means that it will actually bulge out, somehow compress this. Okay, now as it compresses, it will not return back again. Just imagine you have okay, now okay, if it's actually most cases, not in all cases, right? In most cases, in some cases, let me use the word some cases, when you actually apply a normal stress to a solid object, it will actually deform. Okay, it will actually deform, probably uh, bend, and may not return back. All right, but I think when you have some elastic solid, for example, a spiral spring, okay, even when you apply a normal stress on it, once you remove the stress, it returns back to where it's coming from. But some, okay, if you apply stress on them and they deforms, they will not actually return back to their original position. And so this is one way of actually exerting stress. Okay, this is a normal stress. But a tangential stress is a stress you actually you apply parallel to the surface of that object. Okay, so I'm still looking at solid. So when you apply a tangential stress to a solid, you also gonna have a kind of distortion. The solid will also distort. Okay, now if it is actually a rigid solid that distorts, okay, um the one that is not elastic, it will distort to a particular point and it will remain at this point at equilibrium. It will not return back. All right, so it cannot go beyond this, in as much as the force, okay, does not actually exceed um some particular value, right? It will actually distort, okay, this way. Now this is for a solid, but let's now look at exactly how that actually works with fluid. Okay, let's look at a typical example, a liquid. Please pardon me. Typical example is okay. Let's look at liquid in a container. Okay, so if you have a liquid in a container, okay, now on the only way you can actually compress this liquid and it will not deform, okay, is when you actually apply uh let's say the the pressure, right? The stress you apply to the liquid, okay, is going to be perpendicular and it will actually cover the entire surface. Okay, and this particular liquid is found in a container that is not that doesn't have a hole, that is not leaking. Okay, that way when you try to compress this the liquid, it will resist the compression. Okay, it will not compress because liquid don't compress when they are found inside a container. So that is when you actually, when you try to press, um, you are using either a container, okay, to press down the entire liquid down. But if you actually go tangentially, okay, just what I mean by tangentially, just using a small area to touch just one to exert a pressure, okay, uh, at just one end, one side of the liquid, either vertically or horizontally, okay, such stress is called tangential stress, right? It's called tangential stress. Okay, stress that is actually applied at the surface, either horizontally, because it's not. So once you actually you exert such stress, what happens? The liquid will not resist it. It will, rather, the molecules of the liquid will actually be in motion. They will rotate. Okay, they will actually move. They keep on. So they'll keep on. So by the time you actually dip in this particular object, okay, that exerts the stress on this liquid, okay, the liquid will not resist the stress, but rather it will be in motion, it will actually deform. And no matter how little the stress is, okay, unlike the solid that before the solid can actually deform, the stress you apply must be of a substantial amount. But in terms of liquid, no matter how little, even if you use your finger or whatever object to exert that stress, okay, tangentially to the liquid, it will definitely deform. Okay, it will deform. It will not resist the stress. So that is why we actually define fluid as substance that deforms continuously on the application of shear stress. Okay, so please take note of that. So now let's actually, now we already know that fluid, okay, is being categorized into two. We have the liquid, we have the liquid, and we have the gas. All right, so I want to differentiate between these two. Now, let's start with what we know, okay, about these two um, state of matter using kinetic theory. Okay, now you know very well that according to kinetic theory, okay, liquid, okay, is made up of molecules that has weak intermolecular forces, weak intermolecular forces holding the molecules of liquid together. All right. So now that is the reason why liquid can only take the shape of the container. So now, how do I explain that? Anytime you have a container, okay, if you pour liquid into the container, okay, let's say you have a container now that you can actually close, then you now pour in liquid into this container. Because of the fact that the liquid, all right, okay, it's not a rigid body, it will actually come only fuse and take the shape, okay, of the container. Now let's just say that the liquid itself, okay, didn't actually fill the entire container, okay, so it will actually settle. The liquid does, it will settle, okay, it doesn't have random motion, it will settle. Then as it settles, it will actually create a free surface. Now, free surface, okay, is always is is actually created by liquid, okay, in a container because the molecules of liquid of the molecules of liquid, okay, still have some forces that are actually holding that are holding the molecules together. So they don't move around, okay, they don't move around like the gas molecules. So rather, when you pour them into a container, they will settle and only probably take that available space, okay, according to their volume. So now, so in this case, now we are looking at a situation where the volume of the container being greater than the volume of the liquid. So the liquid will settle and of course create a free surface. Now what's a free surface in a liquid? Free surface is the surface, okay, that boundary between the liquid and the empty space. Okay. So this is actually is called a free surface. Why? Because there's no liquid can actually come and occupy this surface. Liquid doesn't have that ability because it is not gas, okay, that is free to move. So it cannot occupy this surface. So it actually creates a free surface. But you cannot get this, right? You can't get this um, when you are dealing with a gas, okay? Now, if you are dealing with a gas, if you're dealing with a gas, okay, let's say a gas molecules, okay, um, gas molecules that is actually being pumped into a container, okay? Now, no matter how small the gas molecules, okay, no matter how small the gas molecules are, they will actually occupy the entire container. Why? The reason being that from the kinetic theory of okay gases, okay, so we know that gases move, okay, in a random motion, so colliding with each other and colliding with the walls of the container, right? And of course, kinetic theory of gases also tells that the volume of the gas molecules is small, is negligible compared to the volume of their container. So which simply means that the small amount of gas molecules can occupy the entire container, okay, because of that random motion. So gas molecules does not actually, they can create free surface, okay, like liquid. They cannot create free surface, okay. The another thing you should know about gas molecules is that they are compressible. So which simply means that if you actually reduce this the container, okay, the container, then they will also confine in that small volume that is actually made available for them. Now we're going to talk about compressibility and other stuff, all right, as we actually proceed. So this is the major difference between gas molecule and and um, and liquid molecules. Okay, so I hope that is well understood. Okay, so now let's actually let's talk about the properties of fluid. Let's talk about the properties of fluid. Okay, there are a lot of properties of fluid, but we are going to concentrate, okay, with this one. We're going to concentrate on this. I think there are five that I will be talking about. So we're going to look at density, after which we'll talk about viscosity. Then we'll talk about specific volume. 4, specific weight. Then 5. Okay, the last but not the least, we'll talk about specific gravity. Okay, so start with the with density. Okay, now density with the symbol rho. Okay, so already I believe that you know the definition of density. So the density of a fluid is actually defined as the mass per unit volume of this fluid. Okay, so by SI unit, density of a fluid is is measured in kilogram per meters cube. All right. So now let's actually compare the density of that of gas and of course liquid. All right. Now before then, density of a fluid is a function of pressure. The density of a fluid is a function of pressure, which simply means that as the pressure of that fluid changes, the density actually change. So density have the ability of actually pressure, please pardon me, has the ability of increasing density or reducing density. Okay, but comparing the density of gas, generally the density of gas and liquid. Now you discover that liquid will always have the density of gas will always be less than the density of liquid. Okay, so what's the reason for that? Remember, density is actually giving us the mass per unit volume. Okay, and you know very well that in a volume, okay, the mass of gas molecules that is occupied per unit volume, okay, is less than the mass of liquid occupied. Okay, the reason you know that liquid will have greater number of molecules, okay, in a particular volume of the container. But for gas, we just have some few molecules of gas molecule that will occupy a particular volume, okay. So that actually shows that in any case, okay, the density liquid is always denser, okay, denser than gas. So please take note of that, okay. Now, as we have already told you that density, okay, depends on pressure. Now, this is only the effect of density, okay. It's the effect of pressure on density is much applicable to gas than liquid. All right. Now, of course, you know from the gas laws, okay, you know very well that pressure, okay, according to Boyle's law, is inversely proportional to volume. So which simply means that if we change the pressure of, if we increase the pressure of gas, the volume of, okay, occupied by the gas molecules actually reduces. Okay, so the change in pressure of gas molecules, all right, we actually change the density, because density is also, okay, density is dependent on the volume. So now that will lead us to two type of fluid. All right, now we have two type of fluid based on uh, compressibility. Okay, we have com compressible, compressible fluid and incompressible. So you need to know between gas and liquid, which of the liquid is actually regarded as compressible, uh, which of the fluid is regarded as a compressible fluid. All right. Now, how do we define compressible fluid? Okay. Okay. Compressible fluid. Okay. Changes density. Okay. changes density with pressure. So as the pressure of the fluid actually changes, the density which changes also change. Okay. So when the change in pressure actually leads to change in density. Okay. That simply means that um such fluid is compressible. So gas are compressible. They are compressible. Okay. So we simply means that their change in density is not constant. Okay. Their change in density is always greater than zero. Okay. Their change in density. Okay. Will I say is greater than zero? Yeah. Okay. Now, but liquid are incompressible. Liquid are incompressible. Okay. So why? Because incompressible fluid, okay, incompressible fluid density remains constant. Remains constant with change in pressure. So of course you know very well that if you have a container containing liquid, there's no way you'll be able to vary this volume of this liquid molecule by applying pressure. Okay, you cannot compress it. Okay, so the entire volumes of um, molecules of liquid remain the same irrespective of the amount of pressure you exert on this liquid. Okay, so we simply say that for gas molecule is incompressible. Why? Because the change in density of gas molecule is always is uh, is zero. Okay, why is the change in density? Why is the change in density zero? Because the the pressure, the initial and the pressure of the of the fluid of gas. All right, please pardon me. The the density of the liquid is constant. All right. So when the density of the liquid is constant, the initial and final density. So initial density is equal to final density. That simply means that the density is constant. So liquid is actually referred to as incompressible. Why? Because it will have a constant density, all right, irrespective of the change in the pressure. So because it has a constant density, the initial density and the final density is always is equal. That simply means that the change in density, all right, the change in density, the change in density of a liquid, okay, is equal to zero. Because the initial density and final density, okay, as the pressure actually changes, is they are constant. Okay, so I hope that is well understood. Okay, so that is density. Now let's discuss the the next property. Okay, so we are going to discuss viscosity. Okay, now simple way of actually defining this viscosity. Okay, the viscosity is defined as friction. Okay, it's a friction now, frictional force. frictional force, okay, that is actually experienced. Frictional force, please pardon me. Okay, now frictional force that occurs in fluid as a result of layers of fluid, okay, flowing against each other or against a surface. So of course you know that frictional force is frictional force is a force that actually opposes motion. Okay, it opposes relative motion between two surfaces in contact. Okay, so now it is called viscosity now because we are dealing with fluid. Okay, now let's say we have a pipe or a channel through which liquid actually flows. Okay, now the liquid that is actually flowing, that is closer to the surface, okay, will have a higher viscosity than the one that actually than the layer above the surface. And of course, so the one that will have the highest speed is the one at the topmost layer. So if we should actually um, look at their increasing velocity, okay, you want to draw the graph of the increasing velocity, the topmost layer will have the maximum velocity, while the one that is flowing, okay, close to the surface will have zero velocity. Okay, so due to that varying velocity of one liquid that is flowing on another liquid, there's always going to be a drag. Okay, just like just like you have a mass moving and that mass is actually connected to another mass. Okay, so and two of them are moving at different speed. So due to the slowness of this mass, it will try to slow down this. Okay, so that's what happened. Okay. So viscosity is simply going to be that, or you can call it a resistance in motion of fluid. Okay, as a result of uh, layers of fluid flowing over uh, the other, flowing over each other, right? So now please take note of that. Okay, so the same way we said that density is dependent on pressure. Okay, now this time around, viscosity viscosity okay, is a function of temperature. Viscosity is a function of temperature. So that simply means that for liquid, okay, for liquid, the viscosity is inversely proportional to temperature. So that simply means that if you increase, if you um, if you want to reduce the viscosity of liquid, you will rather have to increase the temperature. Okay, so for example, most of the oil, okay, probably you use your engine oil, okay, the viscous one. If you want to actually reduce their viscosity, just try to heat them up. If you heat them up, their viscosity actually reduces. Okay, so but in terms of gas, the reverse is the case. Okay, now for gas molecules, their viscosity is directly proportional. viscosity is directly proportional to the temperature. So that means the more temperature, okay, you supply, the more the temperature of gas molecule, the more viscosity. Now the question is, how can you actually explain this? Okay, you know very well that the difference between gas and liquid for any property can always be explained using the kinetic theory of matter. Okay, so even without you reading through the reason why the viscosity of liquid and gas actually varies, okay, with temperature, you can actually explain that. Now let me explain that. Okay, now the difference between these two, okay, is based on their intermolecular attraction. You know very well that for liquid still have intermolecular force. Liquid still have intermolecular force. Okay, that is force between its molecule. All right, but gas don't have any intermolecular force. Rather, you can say negligible. They have negligible. Okay, negligible intermolecular force. So now, so for liquid, when you actually increase the temperature of the liquid, what are you going to do? Okay, now that intermolecular force you will actually create, um because by the time you actually hit the liquid molecules, the distance, okay, the closeness of this intermolecular force, the intermolecular force will actually weaken to some extent. Okay, it will weaken, and as it actually weakens, all right, then the drag of one molecule, okay, will reduce. The drag of one molecule to another molecule will definitely reduce. And of course, you know that the motion of liquid is not random. So once you in the intermolecular force that is binding liquid together actually reduce. So there's this tendency that drag, okay, of one molecule to another will definitely reduce, and there's going to be a free flow. Okay, but on the other hand, this one doesn't have the gas. They don't have any intermolecular force at all, but rather they move in random motion. Okay, so their molecules are actually, they are free. Okay, free molecules, so they move in random motion. Now imagine where you are trying to increase the uh the the temperature. Okay, if you increase the temperature, you are going to end up increasing the collisions. Okay, because gas molecule actually undergoes they collide with each other and with the walls of their container, and the more collision you have, right, the more drag, because collision will actually affect the free flow, okay, of the gas molecules. So if they are actually passing through a pipe, and the temperature actually increases, they will keep on, the collision that will be actually taking place among them will be so high that it will actually lead to drag, and that drag is actually the increase in viscosity. So I hope that is well understood. Okay, so okay, in the next video we are going to talk about the other properties. Okay, we are going to look at the specific volume and the specific weight. Okay, so see you in the next video. Thank you very much.